Hello again, it's Dave Giles here for the final lesson of Cambridge International IGCSE Physics P2 Thermal Physics. So this is the last in the series of the lessons on thermal physics. So today we're looking at thermal equilibrium, and I want you to describe the process of heat transfer and factors which may affect it. So, quick question: what is wrong with the phrase "close the door, you're letting the cold in"? See here, I found a little meme which includes it. So shut the door, you're letting the cold, and Batman slaps that phrase out of him. So let's have a look at what Batman replies with. Thermodynamics 1, heat goes out. So thermal energy is transferred from a region of higher temperature to a region of lower temperature. So you don't let the cold in, you are letting the heat out. So regions in thermal equilibrium have equal temperature. Thermal equilibrium occurs when there's no thermal energy transferred between regions. So thermal equilibrium between two substances in physical contact that have to be touching each other is defined as when there is no longer an exchange of any heat, energy, and both regions have an equal temperature. So here, thermal energy is transferred from the hot region to the cold region. At the moment, they are not in thermal equilibrium because this is 100 degrees Celsius, this is 0. Or after some time, both regions reach thermal equilibrium and no more energy is transferred. So they're both at this, or rather, there's no net energy transfer. So here they're both at 50 degrees, so there's no longer any energy transfer. Question: when will the ice in the water reach thermal equilibrium? So once the ice has melted and the water and the ice is all the same temperature. So basically, once this is melted, it'll all be the same temperature. That is when it has reached thermal equilibrium. Why does the temperature drop more at the start than at the end? So here is a graph showing temperature against time. So this is a boiling cup of water left out in a room, and it loses its temperature. So it loses energy and therefore the temperature drops. So it starts off at 90 degrees, and by the end, it's down to about 21 degrees Celsius. So the reason it drops more at the beginning is because there's a greater difference in temperature between the two objects. So in this case, the two objects are the air and the cup of boiling water. So at first, so by the end, reaches 21 degrees Celsius. So that is the room temperature. So at the start, it starts off at about 90. So the difference in temperature is around about 69 degrees. So the rate of energy transfer is going to be quite quick. However, if we look here at the 5-minute mark, the temperature is now about 25 degrees. The room temperature is 21 degrees. The difference in temperature is only 4 degrees. So the rate of energy transfer is going to be a lot slower. And then you can see when it's reached thermal equilibrium, because this graph goes straight, there's no more energy transfer taking place. Okay, so here, again, not in thermal equilibrium. You've got energy transferred from object B to object A. You've also got some energy transferred from A to B, but most of it is transferred from B to A because B is the hottest object. So after a certain period of time, you can see here, object B is 60 degrees, object A is 40 degrees. Again, there's still most of the energy is being transferred this way from B to A, but there's more going from A to B than previously, but not as much still as going from B to A. When in thermal equilibrium, you have still, again, energy transferred both ways, but the size of the arrow, and therefore the energy transferred is the same both ways. So the temperature will remain at 50 degrees Celsius. And the final part to mention on thermal equilibrium is the transfer of energy from the sun. So we looked at that previously when we talked about infrared. The Earth absorbs infrared radiation from the sun, heating it up. The Earth emits infrared radiation to outer space, cooling it down. When the amount of infrared absorbed and emitted is equal, the Earth maintains a constant temperature. The Earth is experiencing global warming due to an increase in greenhouse gases. So what happens is the Earth's the radiation from the sun is reaching the Earth, heating it up. It can penetrate the Earth's atmosphere, but then when it is reflected from the Earth back up to try and get thermal equilibrium, it can't escape through the greenhouse gases and is then reflected back to Earth. So the Earth is no longer in thermal equilibrium, it is heating up instead. And one more question. Why does heat transfer happen quicker in the bottom picture than the top? So these are both the same object. So same two objects, tin and aluminium. The difference is they are connected at different parts. And the reason it's faster here is because there's a greater area in contact with each other compared to this direction where it's a small area in contact with each other. So the greater the surface area in contact between two objects, the faster the rate of energy transfer. Now, I found two past paper questions, one paper 2 and one paper 4 on thermal equilibrium, and I couldn't find a huge amount, but these are the questions that I found from recent exam papers. So the first one from paper 2, the two samples of the same material have the same mass but different surface areas. Each sample is heated to the same temperature and then left to cool to room temperature. Each sample is allowed to cool to the same final temperature. Which row, so you've got a small surface area and a large surface area, but they've got the same mass. Which row correctly compares the decrease in internal energy and the initial rate of cooling for each sample? So initially, the large surface area is going to cool down faster. So Y is going to cool down faster. However, over time, it will still reach thermal equilibrium because we've got to say it with the room and surroundings. So the total decrease in internal energy is going to be the same. So the answer is therefore D. And in the final part, now this is a 3-mark exam question, so you have to make 3 points. An aluminium dish is initially at room temperature. Boiling water is poured into the aluminium dish as shown in the diagram below. Explain why, after a short time, the dish and the water are the same temperature. So 3 marks. There are 4 potential ways you can get it. So any 3 from the net transfer of energy from higher temperature to lower temperature, or transfer of energy from the water to the dish. The second potential mark, by conduction, or aluminium is a good conductor of thermal energy. Temperature of the water decreases and the temperature of the dish increases. You have to have both of these points for the 3rd mark. And for the 4th potential mark, no net transfer. So I say net because there is still energy transferred both ways. But the overall energy transfer is 0. So no net energy transfer of energy when temperature of dish equals temperature of the water. Okay, so if you got 3 of those points out of the 4, you got full marks. That is it for this unit, thermal physics. I will be uploading the next set of lessons, which are on which are on waves, coming up fairly soon. Thank you very much, everyone, and see you later.